Depending on your encounters with physics, it can be amazing, exciting, or bewildering. Physics is indeed amazing, exciting, and bewildering at the same time. However, physics has also progressed to a point that it is easy to slip in speculations and pass them off as science. In this video, I hope to properly ground you on the nature of physics as a science by exploring its history and its current state. As you may remember, scientific endeavors involve the following: observing, hypothesizing, experimenting. These trio of processes form a cycle that continuously feed new information to the growing body of knowledge that we call science, and occasionally challenge the overarching principles that guide it. For thousands of years, observation and hypothesis making has been done continuously, all in an attempt to rationalize the natural processes that generations of humans have observed. The last process, experimentation, is an innovation. Experimentation basically involves attempting to investigate a phenomenon by isolating it from other intervening factors and then applying acts of measurement while it occurs. One of the first to conceptualize it in the context of science was Galileo. He investigated the acceleration due to freefall. He isolated it by using an inclined plane. He then let metal balls roll down the inclined plane, measuring their time of descent. He discovered that the acceleration due to freefall does not depend on the mass of the falling object. The process of experimentation is one of the hallmarks of modern science. Basically, one can hypothesize and speculate all the way you want. But if a carefully conducted experiment proves it wrong, then you either have to revise it or throw it away. The late Richard Feynman himself said the following: "It does not make any difference how beautiful your guess is. It does not make any difference how smart you are, who made the guess, or what his name is. If it disagrees with the experiment, it is wrong." Interestingly, there is no single experiment to prove an idea right. It only solidifies its stature, but one can expect that a future experiment, even centuries later, can either force its revision or change its bounds of validity. One example is classical mechanics. By 1900s, astronomers have noticed a small but significant deviation of the orbit of Mercury from the predictions of classical mechanics. The solution came from Einstein's relativity, but with its set of postulates that run counter to those of classical mechanics, a redrawing of borders needs to be done. Thus, classical mechanics is no longer universal, technically speaking. Nonetheless, classical mechanics is still well supported in its own bounds of validity, and thus remains as one of the main foundations of physics. From the time of Galileo, physics has progressed so much that one cannot hope to learn everything about it within their lifetime. Instead, all physicists focus on a narrower subfield and conduct their research in their chosen topic. Right now, the four main subfields are required for a physics major to learn. Those are classical mechanics, electrodynamics, quantum mechanics, and statistical mechanics. They are rosy terms for studying a specific set of phenomena in nature. However, none of these are quite arcane nor exotic. They can also involve everyday items. For instance, classical mechanics deals with matter, energy, and motion. It can explain the motion of the planets and the stars. It can also explain how our bicycles manage to stand upright while moving. Historically, classical mechanics was born out of marriage of celestial mechanics and terrestrial mechanics, which are previously thought of as separate and different. Electrodynamics is the result of investigation of the processes behind lightning and magnets. The relentless pursuit to tame electricity and magnetism brought light to our homes and made the modern society possible. Electrodynamics also gave an improbable but ultimately useful discovery: that light is made of disturbances in electric and magnetic fields. This led the way for wireless communication, which includes radio, television, Bluetooth, and Wi Fi. The work in taming electricity and magnetism made it possible for scientists to finally probe the smallest unit of matter, the atoms. In the early 20th century, experiments start giving up results that contradict classical mechanical predictions. This gave birth to quantum mechanics. Quantum mechanics remains supreme in the microscopic world. In its impeccable precision in describing the nature of the atom, quantum mechanics gave us a bridge that connected physics with chemistry. Sometimes, the surprising usefulness of new technology helped further the theoretical exploration of nature. The need to improve the efficiency of steam engines during the Industrial Revolution led to the field now called statistical mechanics. It was a marriage of statistics and mechanics and has brilliantly explained the behavior of gases. Interestingly, it required the existence of atoms, thus helping the discovery of atom in the 20th century. It is best summarized by Goodstein in his book States of Matter. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study statistical mechanics. There are more subfields of physics that now serve as focus of current research. We will focus on four subfields. There are more interesting subfields, and their exclusion in this video does not imply anything about their relevance to our lives. The biggest of these subfields, in terms of the researchers, the number of researchers working on it, is the condensed matter physics. It focuses on the interactions between the atoms that comprise solids and liquids. Condensed matter physics gave us semiconductors, the main materials that make our computers work. Next would be the study of light, optics. One of the results of optical research, lasers, can now be found everywhere. They are used for data storage at compact disks. Lasers are also used to transmit information faster via fiber optic cables. Lasers are also used in medicine, such as in laser eye surgery, to improve one's vision. The quest to probe the atom in the 20th century did not stop at its nature. The atom's nucleus was also explored. This led to formalization of nuclear physics as a subfield. You are more aware of its applications in producing electrical power and in its ability to wipe out millions off the face of the earth. Finally, the frontier of physics was particle cosmology. They are originally separate fields, particle physics and cosmology. Particle physics focuses on probing the fundamental particles that comprise matter and in determining how everything else arises from it. Cosmology is interested with the entire universe, its most fundamental laws, how our universe formed, how it will fare in the future. Scientists eventually realize that these two fields are intertwined and thus are often tackled together, even in popular science. Even with the diversity of these fields and subfields, all of them have these two properties with regards to how they express ideas. First is that the ideas have to be described mathematically. This is one way for a theory to become testable. It has to produce a set of predictions, which can be checked either via observation or via experimentation. This is the main reason that understanding of mathematics is crucial to physics. All physical laws are expressed mathematically in one way or another. Physics also served as motivation for the development of mathematics. For instance, Newton independently developed calculus in order to help him construct classical mechanics. I am sure some of you wished Newton was hit by a coconut in the head instead of an apple. Too bad you still get calculus because a German mathematician named Leibniz was working on it at the same time. Another characteristic of physics is that it also relies on solid reasoning. Physics came from what the ancients called natural philosophy, and the argumentation that you do in analyzing the systems remains important in physics. As often with any other field of study, this led to the creation of a large vocabulary of terms with specific meanings in physics. The main consequence of these two things is that it is relatively easy to masquerade intellectual gibberish by introducing a single word that most people know is associated with physics. Probably the most abused physics word is quantum. This is not helped by the fact that the interpretation of quantum mechanics is still an active battleground. If physics seems like an insurmountable challenge to you because of these things, here's my suggestion on how you would do it. First is to read the material a few times. If you find the prose a bit heavy, you can look for summaries from reputable sources over the internet. You might as well listen to your instructor as he or she describes the basic concepts and relate it to stuff familiar to you. Second, you should read the sample problems and examples with focus on the reasoning behind the steps in the solution. Third, you should try a few problems yourself. There's no learning without practice. Always take down notes and ask your instructors even seemingly stupid questions. I hope you enjoyed watching this video. Another one might be done soon, focusing on one of the topics in physics. Thank you for watching.